subject in this course. The heat transfer mechanism is basically as a result of temperature difference. Wherever there is a temperature difference, naturally we can have thermal energy transport from one point to the other. And if you want to have that heat transfer mechanism in a natural form, then the heat transfer is from the higher temperature to lower temperature. So what is heat transfer? Heat transfer is a physical act of thermal energy being exchanged between two systems by dissipating heat, or heat dissipation, or thermal energy dissipation. So sometimes they use heat instead of thermal energy. Temperatures and the flow of heat are basic principles of heat transfer. The amount of energy, or thermal energy actually, available is determined by the temperature, and the heat flow represents movement of the thermal energy. On a microscopic scale, the kinetic energy of molecules is the direct relation to the thermal energy. As temperature increases, the molecules increase in thermal agitation, manifested in linear motion and vibration. Regions that contain higher kinetic energy transfer the energy to regions with lower kinetic energy. Or simply put, heat transfer can be grouped into three broad categories: conduction, convection, and radiation. And in these three categories, you see that always the heat transferred from higher energy to lower energy naturally, unless you want to use some mechanical devices to push the energy from lower temperature to higher temperature in a cycle. So this is a very good demonstration of three different mechanisms of heat transfer: conduction, convection, and radiation. Conduction we have, and we're going to talk about that more. Conduction is a molecule-to-molecule energy transfer, thermal energy transfer. So that's why when you touch the handle of a pot, you feel hot, although you are not touching the warmer, or you are not touching the stove, you are not touching the source of heat in here. You're just touching and holding the handle, because the energy is transferred from this area, this hot area, all the way up to the handle, even at this point, because we have a molecule-to-molecule heat transfer. Convection as a result of motion plus conduction, and we're going to talk about that. Radiation is as a result of electromagnetic waves that dissipates and transfer the thermal energy in the form of radiation. First, I want to start with the conduction transfer. Conduction transfer transfers heat via direct molecular collision. So there is a direct interaction between molecules when we have conduction heat transfer. An area of greater kinetic energy will transfer thermal energy to an area with lower kinetic energy, and higher speed particles will collide with slower speed particles. The slower speed particles will increase in kinetic energy as a result. Conduction is the most common form of heat transfer also, and occurs via physical contact. Examples would be to place your hand against a window or place metal into an open flame. So conduction is a result of direct interaction between molecules and particles and objects. So let's say you have a wall and you are looking at the wall from the side view. Let's say outside is very hot, it's summer, and inside the house you are at lower temperature. because of the shadow and because of you are inside, because it's a covered space. So, and you have some form of ventilation. The heat transfer is from outside of the wall to the inner side of the wall. Why? Because outside is hot, and that's why we use ventilator inside. Then we need to use HVAC system and cooling system to keep the temperature at a comfort level. This area that you see is cross-sectional area. Let me put it in another slides for the sake of demonstration. So I thought it's better if I draw it for you guys in front of you. Let's look at the so this is inside, and also that's outside. Okay. The area in between these two so now this is sort of the wall that we are talking about. Okay, so this is the thickness of the wall. This is the area inside. So this is, let's assume that this wall is one side of your room. Okay, so in 4 different sides, we have 4 of these. So this is inside, here is outside, and this is thickness of the wall. Okay, so this is the thickness of the wall. This is the wall area inside. The other side on the back that we cannot see is the wall at the outer side. Okay, so this is the area that I'm talking about, and this is the thickness. Okay, thickness of the wall. Let me put another one arrow in here so it would be easier to understand. Okay, so this is the thickness of the wall. Let's say T. Okay, so this is a material, this is filled with the wall material, brick or any other types of substance. So this, what you see in here is basically the T, the delta X is this thickness, okay? So if the heat transfer is molecule to molecule, first of all, we know that the temperature difference is a driving force of heat transfer. Okay, this is the very basic concept. The heat transfer, the driving force for heat transfer is temperature difference. So heat transfer is from outside to inside, because outside is higher and inner side is lower. So temperature difference. What else the heat transfer is related to? Area. This area that I see in here, or backside area. Okay, so this area is, if it's larger, then I get more heat from outside toward the inside. If it's a smaller, for the same temperature of the inside and outside, I get less amount of heat transfer. So area is very important. So area, temperature difference. So let's say outside is 100 and inside is 50. Inside is 70 degree Fahrenheit. And also in another case, outside is 120 and inside is at 70. For the case of having outside at 120 and inside 70, we have more temperature heat transfer rate than when the outside is 100 and inside is at the same 70 degree. So when the temperature difference increases, we have higher rate of heat transfer. And also thickness. Let's say we are using the same material. Instead of this wall with thickness T, I have another wall with larger thickness. So I have thicker wall in here. What about this? What do you think what happens when I increase the thickness of the wall? When the thickness increases, basically I have more materials or sort of more insulation between inside and the outside. So if I increase this thickness, instead of T, instead of delta X, if I have 2 delta X, then there is sort of more insulation between inside and outside. So that means I have less heat transfer. That's why the rate of heat conduction, heat transfer, is correlated with the reciprocal, or inversely is correlated with thickness, not directly. So when the thickness increases, the heat transfer rate decreases. So this is the conduction transfer correlation that I have. But this is correlated alpha. What is the constant of correlation? The constant of correlation is actually K and A. K, conductivity. So area A, temperature difference, temperature outside, temperature inside, and delta X is a thickness. The coefficient of proportionality is K, conductivity. So this is another factor. When conductivity increases, the heat transfer rate in the form of conduction transfer increases. What is conductivity? Conductivity is the material property. So when a substance, when a material, when a medium is more conductive, it means its K is larger. It can conduct the heat transfer from one side to the other better. So let's say you have metal material in here as a wall, iron, and also you have another wall with the same thickness, but the material of the wall is wood. Obviously, for the wall, you're gonna have more heat transfer from outside to inside because the metals are very conductive, but woods are not. So conductivity also is another factor. One more thing is you see a minus sign in here. Let's say, because always you better choose a positive direction for your coordinate axis. So let's say this is my positive direction from outside to inside. If the outside temperature is higher than inside, if is T1 larger than T2, what is the direction for the heat transfer? Is it from inside to outside or outside to inside? Obviously, the heat transfer rate, heat transfer flow is from outside to inside, as this arrow shows you guys. So temperature at point 1 is larger than 2, and heat flow is from 1 to 2. So mathematically, delta T delta X over delta X means temperature difference as I travel for delta X. So if I travel in positive X direction, then delta T is going to be T2 minus T1. Delta X is X2 minus X1. X2 minus X1 is positive. But what about delta T delta X? Delta T delta X, according to this choice of X direction, is negative, because delta T delta X is T2 minus T1. T at X2 minus Tx X1. And T2 minus T1 is negative, because T2 is smaller than T1. So this part, delta T or delta X, for this specific case is going to be negative value. A is a positive scalar value. K is a conductivity of the material is positive. And also we know that Q is positive according to this X positive direction. And delta T delta X is already negative. So that's why I need to multiply it by negative minus sign to get a positive value. And this is always the case. This equation is called Fourier's law of heat conduction, and it was developed by Joseph Fourier, a French mathematician and physicist. So this is called Fourier's law for conduction heat transfer. And actually, it is a one-dimensional conduction heat transfer, because we have two-dimensional and multi-dimensional heat transfer that you will learn in and you will learn in the course heat transfer.